Hi everyone, my name is Gold and I'm here to present my final presentation for ADTA 5560. In this presentation, I would go ahead and be talking about the simple RNN neural network. I would also go over the long-term, short-term memory cells and the core concept of it. And then I would also be showing you the codes that were ran in Python. I would briefly explain what a time series data means, and it simply means time-stamped data with a sequence of data points that are sequenced in a time order. The time series data set I found was gotten from data.world, and it shows the global health nutrition data, and the data set includes 345 indicators. If you can see the Excel sheet, it shows the country name, the codes, the indicators, and the data was collected on a yearly basis from 1960 to 2016. And this just provides the health, nutrition, and population statistics that were gathered from a variety of international sources. Now I'll be talking about the recurrent neural network, also known as the RNN. And this algorithm is it's an algorithm that is used for sequential data. It has been used in Apple's Siri and Google Voice Search, which is something we use in our everyday life. And this algorithm is the first algorithm that remembers its inputs due to its internal memory. And it's the perfect algorithm for machine learning problems, such as the ones where we have to deal with sequential data. Now I would go over to Python, where I would show you what I built in Python using the sine wave dataset. And here is an example. Here in Python, we basically use different libraries such as the NumPy, the pandas, the sequential library, and then the time series generator as well. And then we also use the min-max scaler. Next, we generated the data using NumPy. Here I used the range 0 to 40 and in a 998 data point. And that shows you the array of the data for the x and the y axis. And this also shows you a diagram plotting the x and the y values. And then I went ahead and loaded the data into a pandas data frame and performed EDA just to look at the first 5 values. And then I went ahead to split the data. I used the percentage of 0.2% just for my testing. And then that shows you the test length after it has been split. And then I created a separate testing and training data set, which is standard whenever you're running some of these models. You'd have to split them into a training and test data set. And then I went ahead and looked at the data frame for the first 5. And then moving on, I normalized the data into a range 0, 1 using the min-max scaler. And this is a library that could be used to normalize the data. The reason why we would normalize the data is because we need to convert the data to floats. And over here, we normalize the training data set and also normalize the testing data set. Next, we create a time series generator, which would simply provide a sequence class that could be used to go through a loop. And then we generate the time series of 50. I use the length 50 and the batch size of 1. And over here, it's going to take in the normalized training set, the length, and as well as the batch size. And then we take a look at what the first batch looks like, and then print the X array after it has been normalized or gone through the loop. And then we take a look at what X would predict. And then we would move on to building a simple RNN model. And here in this model, I used one layer. For the feature, I used one, and then I used the sequential model to define the RNN model. And then for my layer, I used 17 neurons. And for my fully connected layer, I used just one. This will be used for like the final predictions. And then I compiled the model using the Adta optimizer and the loss. I compiled the model just to calculate the mean square error and then also fit the model. Over here it shows the model summary after it has been compiled. And then I fit the model using the training data set. And I ran the epoch or the batch size 5 times. And next we would visualize the model's performance after training. And over here you can see that the final validation loss shows it to be a little bit above 0.004. That's the validation loss for this model. And then I went ahead and evaluated the model on the test data set using the input time series, just like I did here in my time series generator. And over here we take a sneak peek at the first 50 data points after it has been generated, because we are looking at it 50 times, so it would generate at least 50 data points. And then moving on, I went ahead and evaluated the model just to see if the model performs well on the test data set and if it's going to make correct predictions on them. And then here it shows the signed value and then also the prediction value. And in the data tests, we also look at the signed value and the predictions, and then we visualize the data on the updated test data set. And here we can see that the prediction closely follows my signed value. Just around here that looks a little bit different, but it's simply making the correct prediction basically. And I would rate this model to be a great model because it's following the prediction is following the actual value of our assigned values. To conclude on the RNN series, I wanted to show this diagram that shows how the RNN works. It's a network that takes the inputs, but not just their inputs. It would also take their current input example that they see and also the inputs that they perceived previously in time. In this diagram, where it shows the BTSX VPE at the bottom, the one at the bottom represents the input example in the current moment. And the context unit here represents the output of the previous moment. So it's simply saying that the recurrent neural network, or the RNN, has two sources of input. It has the present and the recent past, which is combined to determine how they respond to new data. Also, if you've had experience using the CNN or the ANN, we all know they have the input layer, the hidden layer, and the output layer. But the only thing that distinguishes the RNN from those other neural network is that they use a feed-forward network, just like what it shows over here to the hidden unit in this diagram. They use the feedback loop connected to their past decisions, where they ingest or they get their own inputs moments after their inputs. They get their outputs a moment after their inputs. So I just wanted to show this diagram so we can get like a better understanding of RNN. Next, I will be talking about some of the issues that a standard RNN encounter. And the two major obstacles that RNNs have to deal with is exploding gradients and vanishing gradients. First, I would like to talk about what a gradient means. And a gradient is simply a partial derivative with respect to its input. And what this means is a gradient is a measure of how much the output of a function changes if you change the input a little bit. We can also think of a gradient as a slope of a function, meaning the higher the gradient, the steeper the slope, and the faster a model can learn. A gradient simply measures the change in all the weights with regard to the change in error. So with that being said, training or using an RNN to train a model or to train a data set, we encounter the exploding gradient and the vanishing gradient. And what an exploding gradient simply means is when an algorithm without a reason assigns a high importance to the weight. Fortunately, to solve this problem, we can easily truncate or squash the gradient. Another issue an RNN faces is the vanishing gradient. And what a vanishing gradient simply means is when the values of your gradients are too small and the model stops learning or takes way too long as a result of doing this. This was a major problem, and it's a much harder problem to solve than the exploding gradient. Fortunately, to solve the vanishing gradients, we introduced the concept of the LSTM, which is the long short-term memory, and we would explore that further. The LSTM network is one solution to the issues of vanishing gradients and the exploding gradient. And in the LSTM, we have the input, output, and the forget gate. One thing to note is that the LSTMs are an extension for the RNNs, which basically extends their memory. The LSTMs enable the RNNs to remember their input over a long period of time. And because the LSTMs contain information in the memory Just like our computer, they can read, write, and delete information from its memory.